Okay, so we're on 3.7, inclined planes. So recall that in chapter 3 we're looking at acceleration, and in 3.7 we will briefly consider acceleration due to gravity. Okay, and we know that acceleration due to gravity is constant. It's a constant number, but Galileo didn't know that, and he wanted to find out. He was studying acceleration due to gravity, and he actually ended up concluding that acceleration due to gravity, meaning free fall, was constant, but he couldn't use high-speed video, high-speed cameras that could take pictures at every interval and then measure the distances between them and see that they're actually increasing every time, so to conclude that there's an acceleration. What did he do in order to conclude that acceleration due to gravity was constant? What he did was he set up inclined plane experiments. So he had some kind of piece of wood or something like that, and he inclined the plane at a certain angle, a fixed angle, and then he allowed a ball to roll down. And then he measured the time it took to get to, say, x1. He measured the time it took to get to x2, to get to x3. So he's measuring a distance and a time to get to that specific distance. He's measuring another distance and the time it takes to get to that distance. And he measured another distance and the time, etc. And what he found for this kind of shallow angle, acute angle, okay, is that the ratio of the distance to the time it takes to get to that distance squared is constant. So x1 divided by t1 squared is equal to x2 divided by t2 squared is equal to x3 divided by t3 squared. This is a constant. So he concluded, which is what I just said, when a ball rolls down an incline starting from rest, the ratio of the distance traveled, that's the distance traveled, to the square of the amount of time needed to travel to that distance is a constant. Okay? So, where have we kind of seen this before? Well, we know from this equation, where does this equation come from? We know that this is a constant acceleration equation. This is position as a function of time. So it's a constant acceleration problem. X final is x initial plus vt plus half at squared. Remember this equation. If your initial position and initial velocities are 0, then you end up with this. And if you divide the x divided by the t squared, you get that same ratio that Galileo found. And basically, what he was doing was he kept increasing this angle, and for every angle, the ratio remains constant. Ratio is constant for every angle. And the ratio increases as the angle increases. So as this angle is increasing and increasing, the ratio of x over t squared is also increasing. Okay? But the point is that it's increasing, but for every fixed angle, that ratio is constant. So if you end up with a 90-degree angle and you drop this ball down like that, what he concluded was, as you keep increasing it, if it's constant for every specific angle, then the acceleration for free fall for this 90 degrees will also be constant. Okay? So he concluded that also for free fall, there would be a constant ratio of x over t squared. Okay? All right, see, I'll conclude this in the next video.